So now let's talk about how water boils. Now, this is going to be an interesting movie, and as a matter of fact, we'll make a sequel to it, just like Sharknado, I guess. So let's talk about how water boils, because actually it's interesting. If you take water and you put it in a piston cylinder device and you hold the pressure on it constant, and you start adding energy to the water, let's say you start the water out at 20 degrees Celsius and 1 atmosphere. Well, as you add energy, say you just put a candle under it like I've shown here, and you're adding heat, okay, so you're transferring energy into the water, what will happen is something that makes sense. There will be what's called a sensible change in energy. The temperature goes up, right? Not really a big surprise. But something interesting happens after you reach a pressure of 1 atmosphere and 100 degrees Celsius, or what you would know as the boiling point of water. What happens is you can continue to add energy, but the temperature will no longer change. Rather, what happens is the water boils, right? Not all of it at once, but drops of water will start to boil off and become a vapor, become a gas. And as you continue to add more and more heat, or transfer heat would be a more proper way to say, you add energy to the system, you'll just generate more and more vapor. More of the water will boil off. Now if you just pull the candle away and insulate it where no energy crosses the system boundary, and so now you have a closed system, and in fact an isolated system, well then it'll just remain with the amount of liquid that was present and the amount of vapor that was present. Now understand, we're assuming equilibrium states along the way. So it's already at equilibrium. It's not like there's a hot point at some region of the piston cylinder device where it's going to transfer more heat and boil off more water. So we'll end up with two phases, a liquid and a vapor phase, and they're called saturated. And the reason they're called saturated is because it seems like that the liquid water is saturated with heat. It's got just as much heat as it can take without changing phase. Okay, so it's called a saturated liquid, and the vapor is called a saturated vapor because if you go the other way, if you take this piston cylinder device and now you start cooling it, you start extracting energy from it, what will happen is the vapor will start to condense out and you'll make more and more liquid water. Now be careful in this course, because when I say water, I don't necessarily mean liquid. I could mean liquid, I could mean vapor, I could mean gas, right? Either one. So be careful about that when I say water, because sometimes I don't even think about it anymore and I just say water and I mean water vapor, for example. Now let's go back to our experiment. We're in state 3. We've got some vapor, we've got some liquid. Now let's keep adding energy to this system. What happens? Well, water keeps boiling off. More and more mass moves from the liquid phase into the vapor phase. Now as we go along, we'll eventually come to a point where we run out of liquid water. All of the water will finally boil off and be in the vapor phase. Now at this point, it will still be at 100 degrees Celsius and 1 atmosphere. Those two properties will not change at all. What will happen after this, if we continue to add energy, is now the water will begin to go up in temperature again. Okay, so the vapor will start rising in temperature. Now the change in temperature, those changes are called sensible changes, but the change in phase is called a latent phase. And latency is something you may be familiar with, especially if you're a video game enthusiast or if you're an audio enthusiast on the computer. You may know something about latency. It just means a delay, basically. So it's called a latent transformation because it's like we're waiting for the temperature to start changing again. So some terminology to make sure we get it right. The liquid at 20 degrees Celsius, 1 atmosphere in state 1 is called a subcooled liquid or a compressed liquid. And all that means is that it's below the temperature at which it could begin to boil. Once it gets to the point where it could boil at 100 degrees Celsius, we call it a saturated liquid. In other words, it could vaporize. Now if we add a little more energy, some of it will transfer into the vapor phase. Now once we have both vapor and liquid, we call it a saturated liquid vapor mixture. Now be careful of this terminology also, because mixture doesn't mean that it's mixed up real well and we got vapor bubbles in the liquid. It doesn't mean that. I mean, it may be, but a lot of times we think about it as those two phases being totally separate from one another. So that's a saturated liquid vapor mixture. Once we get to state 4, now we've got only saturated vapor. The last drop of liquid has boiled off, and we have a vapor that really is about to condense if we extract energy. But if we continue to add energy, then the temperature goes up above the boiling point at that pressure, and it becomes what's called a superheated vapor. And as you continue to add energy and the temperature goes up farther and farther, it's still a superheated vapor. It's above the temperature where it could condense out. Now notice that during the process of boiling, the phase change process, we observe constant temperature, and one of the reasons that is that we have a constant pressure during that time. And it turns out we can only have 1 degree of freedom. So I'll talk to you more about what that means in just a little bit. But the temperature and pressure actually depend on one another during this transition time. Now you can plot the saturation temperature versus pressure, or the saturation pressure versus temperature. In other words, there's a magical temperature given a pressure where the water will begin to boil. And it's not really magic, obviously, but it seems like it. If you change the pressure, then the temperature at which the water begins to boil changes as well. So there's a relationship between the two. As a matter of fact, in the back of your book are what are called saturated tables. So you should grab a tab at this point. This is the first tab I'm asking you to add to your book. Table A4E and Table A4 are two tables that you should tab right now. So that's page 890 for A4E. I don't have the A4 page in front of me. What you'll notice about the back of your book is that the appendices are first metric and then English units, but it's the same thing in both with a couple of really small exceptions. So for now, go and find those two pages and make sure you tab them saturation tables, okay? Because that's what they are, or steam tables. That's the way we'll refer to them as well. Now, if you notice, the first column is temperature, the second column is pressure. Now, if you turn the page I think 1 or 2 pages, you'll notice that you'll have pressure as the first column and temperature as the second. Turns out that the data in those two sets of tables are exactly the same. Well, they represent the same thing, but they're for different data points, okay? But they're representing the behavior of water, or the chemical H2O. Now, if you take the temperature and pressure data and plot them versus one another, you'll get the graph that you see down there in the lower right-hand corner of my slide. And so a lot of times, well, I struggled trying to understand what is saturation temperature. Well, it's nothing more than the temperature at which boiling will occur given a particular pressure. And so those two together are called a saturation pressure and a saturation temperature. I wish they were called a saturated temperature pressure pair, because that's really what they are. Or a saturation pressure is the pressure at which boiling will occur given a temperature. Okay, so they go hand in hand. They're not one separate from. You can't have a saturation temperature at any old pressure. That doesn't work. Okay, they're really a pair. Let's talk about latent heats a little bit. What is a latent heat? Well, remember we said that during boiling we had to add energy to the liquid water to get it to change phase into gas. So that process, the amount of energy that we have to add to completely transform all the liquid into vapor, that is called latent heat. It's heat that we have to add, or energy we have to add to cause the latent transition from one phase to another. Now, it turns out that there's actually two latent heats of particular interest to us in this class, one usually more interesting than the other. The first one is the one you probably think of, the liquid to vapor transition. If I take a pot of water and I sit it on the stove, how much energy do I have to put into that pot to get all the liquid to change into vapor? Well, of course, the more water you have, the more energy it's going to take. But if you look at it on a specific basis, or a per unit mass basis, turns out it's 2,257.1 kilojoules for each kilogram if we're boiling at 100 degrees Celsius. And of course, if we're boiling at 100 degrees Celsius, that's the saturation temperature, therefore the saturation pressure is 1 atmosphere. Okay? Those two again go hand in hand. So I should have something that says 100 degrees Celsius, comma, 1 kilopascal, well, not 1 kilopascal, excuse me, 1 atmosphere, or 101.325 kilopascals. That's the amount of energy that it takes to boil off 1 kilogram of water. Or you could say it this way: if I have 1 kilogram of vapor, how much energy do I have to pull out of it to get that vapor to go back to the liquid phase? Well, it's the exact same amount. It's 2,257.1 kilojoules per kilogram if we're at 100 degrees Celsius for our boiling process, or our condensing process in this case. Now, it turns out that there's also a latent heat of fusion. Now, that's how much energy you have to put into ice to get it to transform into liquid, to change phase. And that's actually less. It's 333.7 kilojoules per kilogram for water at 1 atmosphere. Okay. So actually, that's what you do when you take a picnic basket and you put ice in it, right? Or a cooler and you put ice in it. What you're really doing is admitting that heat's going to transfer into that cooler, right? And it's kind of like the ice takes the bullet for it, okay? It's like the ice absorbs that energy, remains at 0 degrees Celsius, so the potato salad doesn't make everybody sick, right? But it changes phase in order to absorb the energy yet remain at the low temperature. So we use ice or other chemicals in our coolers in order to absorb energy, transform phase, and by doing so prevent our food from going bad, because at lower temperatures bacterial growth is slowed. And that's what we're trying to make happen, so we don't get sick from the food, right? Picnics are great until you come home with a bellyache. Now, we could perform this experiment at several different pressures. So the one we performed was at 0.1 megapascals approximately. That's about an atmosphere. So you'll notice I'm pointing to that second peak lineup, and we began with a subcooled liquid. And so what I'm doing here is plotting temperature versus specific volume. Now remember, specific volume is a per unit mass volume. It's really the inverse of density. If you like thinking about density, this is just the inverse of it. It's 1 over the density. So if we plot points along this, if we plot temperature versus volume, we have a system, we're measuring temperature, we're measuring volume, and we plot a point. Well, here's our first point of a relatively low volume, right, because it's all liquid, and a relatively low volume per kilogram. It's all liquid, and it's at 20 degrees Celsius, a relatively low temperature. Now, the first point we reach is the saturated liquid point. Now, when you add energy to water, the temperature goes up from, say we started at 20, we're going up to 100 degrees Celsius, so it's not a surprise that we've moved up on the temperature axis. But we also have to move up on the volume axis, because actually the water will expand a little bit. Not a whole lot, but some. Now you'll hear a lot about my famous boiler system. It turns out I actually heat my house with wood. Someday I want to put in something called a geothermal system. It's also known as a ground source heat pump. But that's pretty expensive, and I just haven't put the money into it yet. But right now I heat my house with wood, and I've got it's not like I'm belching out smoke into the neighborhood. I live in a fairly rural area, and so my neighbors don't mind. It does actually emit smoke sometimes when it's not burning right, but the way the boiler is supposed to work is it has an upper and a lower burn chamber, and what it does is it generates smoke, and then it adds superheated air to it to burn the smoke. If you look, there's actually a nozzle that goes between the upper and lower chamber, where the wood is actually in the upper chamber. And if you look, I actually added a sight glass in the bottom, and I had to use quartz because it gets so hot, so I could look in and see the flame that's shooting down through that nozzle. It looks like a blowtorch. As a matter of fact, sometimes the flame is so hot it's purple. I don't know if you know this, but orange flame is relatively cool. Now, you'll burn your finger in it, obviously, but it's a relatively cool flame, whereas a blue flame or a white flame is a very hot flame. Well, purple's not quite there, but it's still very hot, a lot hotter than you normally see in just a simple wood stove. So it's a wood gasification stove, and it's much more efficient. And what that means to me is I don't have to load so much wood in the thing, you know, and it gets tiring after a while. Plus, I'm burning more wood than I really want to have to go out and collect. So if I can burn it efficiently, that's good for me, because smoke is actually unburned wood. Okay. Anyway, that's kind of beside the point. I was talking about boiling. So in addition to the boiler, I've got a couple of tanks that I buried that store 1,000 gallons of water. Now, this is not water you would want to drink. This is just water where I can burn in the boiler. I can burn a whole load of wood and dump that energy into the water. So you see, the problem is, when I burn wood, there's so much wood in the container, I can easily overheat my house in the wintertime pretty quickly. I don't need all of the energy that is represented by a stack of wood, but on the other hand, it's hard to get a small stack of wood to burn hot. And so what you really want to do with this boiler system is you want to load it up with wood, and not really fill the chamber completely, but put a good amount in it so that you can get it going and get it running nice and hot, because when it's running hot, it's running really well. It's burning efficiently. The stuff coming out of the chimney is absolutely clear, and you can't even tell that the thing is running. Okay? So what you want to do then is burn hot and fast and as long as possible, but you got to have somewhere to put all that energy, right? Energy can't be created or destroyed, so what do you do with it? Well, what I use it for is to heat up water. In fact, I'll take water from about 50 degrees, that's a local ground temperature roughly, up to about 200 degrees. And then I don't have to load the boiler overnight, right? I don't have to load the boiler for a couple of days sometimes, especially when it's fairly mild out. And that gives me it's kind of like a capacitor in the electrical world, or a flywheel in the mechanical world. It's a place to store energy to kind of smooth out demand. Okay, so I put all this energy into these tanks. Well, wait a second, 1,000 gallons of water. If you change the temperature of that water, do you suppose it expands? Yes, it does, and that's the whole point of my story. Just like here, as you add energy to that water, it changes size. Now, It's not much. In the 1,000 gallons that I have, I've calculated that the volume changes by about 50 gallons or so. But that's still significant. As a matter of fact, it would literally blow my pipes apart if I didn't have somewhere for that extra water to go. So I have what's called an expansion tank. And the expansion tank has a diaphragm in it. And that diaphragm just has air pressure on one side and water on the other. And as the water pressure increases, because it's trying to expand, it compresses the diaphragm. The air pressure goes up a little bit, but it can compress the air fairly easily. And there's some place for all of that extra water to go. Anyway, long story. But I will talk about the boiler more, so I thought I'd introduce you to it now. So we're at that second point. We're at that knee in the curve where now the water is saturated. It's a saturated liquid. In other words, as we add more energy to it, the temperature cannot change because we're holding the pressure constant at 1 atmosphere, or about 0.1 megapascals. So we relentlessly add energy, and what happens? Well, there's a phase change. And so you see our third element here from the sequence I showed you before, where now we have some saturated vapor and some saturated liquid that are in equilibrium with each other. If we stop adding or removing energy, it'll just stay as it is. Now if we keep adding energy, what will happen is the amount of liquid will go down and the amount of vapor will go up. So the effective volume of the whole system is getting bigger and bigger. Okay, so we're moving to the right on this curve, but the temperature is not changing. We're in that latent transformation, the phase transformation portion of water boiling. Eventually we'll get to the point where we run out of liquid water and it will all be vapor, and we'll be at this other point in the curve where the slope changes significantly. So now we're at that final point where the temperature has not changed for the last time, and now when we start to add energy, now the temperature has to start going up again, and it turns out the volume will go up as well. So we end up in the superheated region. Now notice we can perform this experiment over and over and over at different pressures, and we get a family of curves like you see here on the TV diagram. Now we can kind of play connect the dots with these, right? I mean, look at it. It's pretty obvious that there's all these points on the right-hand side and the left-hand side, and if we connect those together, we get a shape called the vapor dome. Notice that this shape separates out the phases of the diagram. To the left-hand side we have all liquid. Under the vapor dome we have a mixture of vapor and liquid, and to the right it's all superheated. And you might look at this and say, well, there seems to be this interesting thing that happens up at something called the critical point. Well, at the critical temperature and pressure, what happens is zero energy is required to transform from the liquid to the vapor phase. You're going along just fine. Everything's liquid, 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 and you add just that little bit more energy and boom, it's all vapor. So it's a zero amount of latent heat. The latent heat of vaporization is zero at the critical pressure and temperature. Okay? Above that, you don't really see the transformation. You can't really see a difference between the liquid and the vapor. It's like it just it changes, and you don't really see it change significantly. It's hard to see a boundary between the liquid and the vapor. So we've kind of played connect the dots. Now we've discovered this thing called the vapor dome. Let's try to understand that vapor dome. Say we invert it, right? So let's make the experiments the dotted lines, and let's make the vapor dome the solid line. Now on the left-hand side, from the critical point down on the left-hand side of the vapor dome, that line is called the saturated liquid line, because that's all the points at all the pressures where we would have all saturated liquid about to boil off our first bubble of vapor. And on the right-hand side, the critical point down on the right-hand side is called the saturated vapor line, because that's the last point, if we're adding energy, where the temperature will no longer change. After that, the temperature has to start going up. So that's the names of these things. We've got the compressed liquid region on the left, the superheated vapor region on the right, and the saturated liquid vapor mixture region in the center. Now that was so much fun, kind of like Sharknado 1. Let's make a Sharknado 2. Let's see how water boils part 2, right? If you're not asleep by now, this is pretty much guaranteed to do it. What if we do a similar experiment, but this time instead of holding pressure constant, let's have some type of control where we hold temperature constant. Now we're not going to hold temperature constant by adding or removing energy. As a matter of fact, we're just going to keep relentlessly adding energy like we did before. But now we're going to have a pile of sand on top of the piston, and we're going to remove some of that sand. We'll take some weight off and control the pressure that way. Now, if we're at 1 megapascal and 150 degrees Celsius, we will be in the saturated liquid region. As a matter of fact, open your book to the saturated tables. You should have marked it earlier, table A4, and I'm sorry again, I still don't know the page number. Now look up a temperature of 150 degrees Celsius and look at the pressure you read off. You'll read off, I think, 0.47 some odd. It rounds to 0.48. So if we're at a pressure of 1 megapascal, that means we have excess pressure that's preventing boiling. So we're not at the saturated temperature, saturated pressure pair that we need for boiling to occur. We are in the subcooled liquid region, or the compressed liquid region. Now understand now where those terms come from. Subcooled liquid refers to, given a pressure, the temperature is too low to boil, but the compressed region refers to, given a temperature, there's too much pressure for it to boil. Okay? That's why it's called either one. Now as you remove sand from the top of this, what will happen is you will eventually get to a lower pressure. The temperatures remain constant at 150 degrees even though we have added energy to the water. Okay? We finally reach that point, that pair where the temperature and the pressure are both now saturation temperatures and pressures. And now we don't have to remove sand in order to keep the temperature constant at 150 degrees Celsius, even though we continue to relentlessly add energy to the system. As a matter of fact, the system will naturally stay at 150 degrees Celsius as long as we leave the sand, and actually the piston weight, constant, so that the pressure is 0.48 megapascals or so. The actual number is in your book. It's a little more precise in your book than what I have in the slides. Now, as we add energy, now let's go back actually to the beginning, okay, when we were in the subcooled or the compressed region. As we added energy, even though the temperature wasn't changing, because we were pulling pressure off of it, we still call this a sensible energy change. We had to change something, and so that makes sense for the system to maintain 150 degrees Celsius. But again, from the saturated liquid all the way through to the saturated vapor phase, this transition is called a latent transition again. Okay, there's still a latent heat of vaporization here. Okay. Now we will eventually boil all the water off from the saturated liquid vapor mixture. All of that liquid will eventually go into the vapor phase as we continue to add heat or add energy. And we'll finally get to a point where there is no more liquid. It is all boiled off. It is all in the vapor phase. If we continue to add energy at this point, now we will have to start pulling more and more sand off and reducing the pressure. And so if we get to a point where the temperature is 150 degrees Celsius and the pressure is 0.01 megapascals, which is roughly an atmosphere, no, that's less. 0.1 megapascals would be an atmosphere. Okay, then we're in the superheated region. But just for fun, I could have put 0.1 megapascals there and it would have still been correct because that would be in the superheated region. Let me prove it to you. Go to the saturated tables again, but this time instead of going to the temperature tables, which is A4, I believe it's A5. Okay, it's just a couple pages past. And you'll notice that it's the pressure, saturated pressure tables because pressure will be the first column. So look up yeah, this will work. Look up 1 atmosphere or 101.325 or roughly 100 kilopascals. Should be good enough. 100 kilopascals is fine. What you'll notice is that the temperature has to be pretty close to 100 degrees Celsius, which shouldn't be a surprise, for the properties in the table to be useful. If the temperature is far above that, then you must be in the superheated region. Now, one of the things you really need to learn to use the saturation tables for is to decide, are you in that saturated vapor mixture or saturated vapor liquid mixture region? Are you in the superheated region, or are you in the liquid region, the compressed liquid region? So I'm trying to teach you along the way how to do that. You'll see more of this in the example problems. So we have similar terminology to what we had before. There's constant pressure, of course, during the latent transition. And we've got the, I went too fast, we've got the superheated and subcooled regions. Now we can draw a PV diagram. Remember before it was a temperature versus volume diagram. Now we can draw a pressure versus volume diagram where each of the experiment lines represent experiments done or performed at constant temperature. And what you'll notice is in these experiments, as we add energy, we have to decrease the pressure, right, for the temperature to remain constant and for us to remain on that constant temperature line. So it makes sense that the volume's going up because we're still adding energy, the water is still expanding, But in order to maintain the temperature, we've got to go down in pressure. So we're moving down and to the right on those dotted lines. We finally get to a point, just as we did before, on the saturated liquid line, where we have a saturated liquid. It's about to evolve the first bubble of gas. If we continue to add energy, we move through the saturated liquid vapor region at constant pressure and constant temperature, by the way. Remember, these are still lines of constant temperature. And then we eventually get to the point where there's no more liquid, it's all vapor. We continue to add energy and we move into the superheated vapor region. But as we move into the superheated vapor region, we have to reduce pressure farther and farther to maintain the temperature constant. And of course, since we're boiling off liquid, the average volume of the system increases. And as we continue to add energy to the gas in the superheated region, the volume continues to increase as well. Now we can extend this to include another phase. We can include the solid phase of a substance as well. As a matter of fact, we can do this for water, we can do this for other substances, because other substances also have solid to liquid to vapor transitions. Now, some substances contract when they freeze. So what they'll do is they'll go, if you take a certain volume of liquid and you start cooling it such that it begins to freeze and crystals begin to form, it'll shrink from the very beginning. But water's a little bit different. Water actually expands a little bit, and then when you finally reach all solid, well, then it starts decreasing. Okay? So to see this, it's a little bit difficult to see or to understand what happens to substances that expand on freezing like water. Let's start with substances that contract on freezing. You see the vapor dome there that includes liquid, liquid vapor, mixture, and vapor. But there's actually a triple line, which is a line of pressure which below you can have solid and vapor in equilibrium with each other. And there's also these vertical lines where the volume just doesn't change hardly at all, where we're going from liquid to solid, okay? And then from that solid-liquid mixture, that's that region in between, those two vertical lines, well, eventually we reach the solid vertical line where we have only solid, and then we have the solid region to the left, which we could continue to cool, and it would continue to shrink, right? But it's still solid. It's I guess you could call it a subcooled solid. It's not near the point where it could go into the liquid phase. All right, what about substances that expand on freezing? Well, this is a little more difficult. Try to hang with me here, and in just a second I'll show you a figure that I think will help quite a lot. If you have water, just liquid water, okay, we're in the liquid region, so we're to the left of the vapor dome, and you cool it down, what will happen is it will shrink, right? So its density increases, its specific volume decreases. Eventually you'll reach the dotted line that's angled a bit, okay? When you reach that line, what has happened is you're at the point where you begin to make solid ice crystals in the liquid. And as you continue to freeze more and more crystals, those crystals take up more space. They are less dense than the water, and the average density of the whole system begins to creep back down, right? Or the specific volume begins to creep back up. So we've reached that dashed almost vertical line, and now we're moving to the right. Our average specific volume is actually increasing. The density is going down because we're forming ice crystals. Eventually we'll reach the almost vertical solid line, which is where the water has all become solid, and then if we continue to cool it, then its volume will start to go down again. Okay, its specific volume will start to decrease, because if you take solid ice and you cool it farther, its density will continue to go down. Now there's one other substance I know of that behaves kind of like water in that it expands on freezing. I think it's bismuth, but I can't remember. You can look that up if you're interested. Now we could look at a pressure versus temperature diagram. We've looked at PV diagrams and TV, temperature versus volume, pressure versus volume. What about a pressure versus temperature? Well, we've already looked at part of this, right? Because we had a line that was made from the saturation pressure temperature pairs, right? And so all we're doing here is we're adding in the solid region to that line, okay? And really, to the right of the line are liquids or vapors, depending on whether we're in the melting region or vaporization region, and to the left is solids. Okay. Now, of course, substances that expand on freezing have a different line, a different melting line than substances that contract on freezing. Now, this may not make a lot of sense to you, okay? It seems kind of strange. Let me show you what really tied it all together for me. The PVT surface is something I really prefer. This is what you would see in 3 dimensions. Now, to understand this, you have to understand that the properties of the substance cannot exist within the solid of these graphics. It has to exist on the surface that you see. So you could have a vapor-liquid mixture under the vapor dome, which would be just below the critical point, above the triple line, and on that entire surface that's at an angle looks, I don't know what it looks like, it looks kind of like an end of an egg. Okay, it's just a flat surface. On that surface is where you could have different combinations of pressure, volume, and temperature that particular substance allows. Okay? You wouldn't go into the substance, it would just be in that region. You see the region, though, beyond it, above the critical point, where we've got the label liquid, gas, and vapor. Okay? In that region, that's where on that surface, that's where the substance could exist at relatively high pressures or high temperatures, or relatively high specific volumes in particular. So notice we've got a pressure, volume, and temperature axis, and we don't really mean volume necessarily, really we mean specific volume, per unit mass volume. Now below the triple line is the solid vapor mixture region, where solid and vapor can be in equilibrium with one another. And you see that small, almost vertical slope. Looks like it'd be fun on skis, or actually very scary on skis if you could ski down that slope. Well, that's the area where solid and liquid are in equilibrium with each other. Now, unfortunately, you can't really see it on the substances that expand on freezing diagram, but that shape I just pointed out, that slope, that solid liquid equilibrium area, that's something that also exists on the other PVT surface. It's just back behind, okay? So you can kind of see it back there if you imagine that. Okay, it's turned around, if you will. So basically, the substance has to exist at some point on this surface. And if you go back and you look at some of the things we've developed so far, you'll recognize all we're really doing is taking projections, looking at this surface from different directions. And the shape of this surface is simply determined by the nature of the chemical that we're testing. Now, water has its own unique surface. Every substance has its own unique surface. How is that surface determined? Good question, I don't know. But it is something we can measure, and there are relationships between the pressure, volume, and temperature. Because understand, once I give you a unique combination of pressure and temperature, say it's in the gas phase, you can tell me what the volume is, can't you? Because that would identify one unique slice, and therefore one point. Wait a second. Let me think through that for a minute. So we'd one pressure and one temperature. Where that intersects is a line. Yeah, that line is only going to intersect with the surface at one point if we're in the, say, the liquid, gas, and vapor region. Now obviously on the solid vapor region and the vapor liquid region, that line could potentially intersect several different points.